Good evening, everyone. Welcome to Lesson 2 of Unit 2 for Statistics. In our first lesson in this unit, we looked at the qualities of center and shape for a data set. Now, of those fancy three S's of stats, we have one more to take a look at, and that's spread. And that's what this lesson is about. So, all three things put together, shape, center, and spread, form a good description of pretty much any data set that we can visualize. And when I draw a graph, it allows me to visualize in words, allows me to express some of the thoughts of the things that I visualize. But as we said earlier in class, was that sometimes our visualizations have some wiggle room, and each person can visualize different things in a data set, can interpret the data in their own way, especially when you have kind of borderline-ish data. So we use a situation of data that is slightly skewed. So one person could say that a data set is slightly skewed. One person could say that that data set is mostly symmetrical. And they're both kind of right, but you know, is there a line that we go with? Do we go like, majority rules from a jury or something like that? I don't know. So instead, one way that we can sort of mitigate those discussions is to have a numerical basis to base our opinions on. So in lesson one, we looked at the difference between mean and median. And we said, well, the further apart that the mean and median are is a pretty strong indication that a data set is skewed. And if the numbers are very close, we can say that they're approximately symmetrical. And turns out that's a very good indicator. And that uses, so now we have the numerical measure of center to inform a numerical measure of shape. So all we need now is a numerical measure of spread, right? So the range, we've used that already, right? So for example, if I look at the classes here that are on this page, we have two classes taking the same exam, 6 students in it, right? So if we have class A and class B and they're taking this exam, one way that we can measure this data is with range. So class A ranges from 50 to 96, which is like a 46-point range. And then class B ranges from 64 to 81. And that is a 17-point range, 17-point range. So which class is more variable? Class A, definitely, right? So at first, it seems like, well, that's it then. Is it just range? Sorry for the pause there. I just realized I never actually plugged my stylus in. So I'm sitting here talking and realized I had nothing to write with as I was about to write. Okay, so looks like we are good now. Let me make sure. Hello. Perfect. All right, we can go. So what I was mentioning before was, range is one measure of variability, right? So, but is that it that we can think of? Because here's the problem with range, right? Range only involves the first two numbers, or the first number and the last number, I mean. So it only really looks at the endpoint. So these classes, the numbers in the middle, these four here, and these four here, those numbers could be quite a bit different. And those numbers could be all crunched to one side. So maybe for class A, maybe 5 people failed and one person got a 96. Or maybe one person failed and 5 people got an A, or somewhere in between. Class B, same thing, right? So these numbers seem fairly evenly spread at the moment. But now our question is, do we have a way to quantify not just variability in terms of the range, but variability throughout the entire data set? That's what we're going to look at here in this lesson. So notice with these data sets, you can go ahead and calculate the mean and median, right? And you will find that they have the same mean and median of 73. So, okay, now same mean and median, that means the data set should be pretty symmetrical. Well, are they? They certainly look like it, right? They look to be pretty evenly spread to me. So we'll start with that. Now, if these were a little more skewed, would the mean and median be different? Sure. But just the mean and median are not enough to decide on spread because the numbers are a lot different but still have the same mean and median. So range is important, or variability is important. Okay, so here's one way that we can measure spread, right? We're going to find what's known as a deviation. So the deviation for a data set is measured as the distance from the mean. So a deviation, let's write this out here, deviation is equal to x minus x bar. So x referencing a data point, right? Now we do know from our work earlier, we said that x by itself represents the data set. We can also take it to represent a member of a data set. So the value of x represents any point from class A, or likewise could be from class B as well. So we are taking each of these and we're subtracting the mean. But we already know that for both cases, the mean is 73. And that's for each class separately and for the total. So we're looking at each class separately. We're subtracting 73. Now, the reason why you would do this is now look at how the numbers are arranged now. -23, -12, -4. So look at how well they are spread on both sides of average. That's pretty good. This data set, class A, is actually not almost, it's perfectly symmetrical. Class B is actually 1 point away from being perfectly symmetrical. Kind of interesting. And that may or may not play a part. So we think about, what does it mean? We have one data set that's, perfectly symmetrical, so we understand the mean and median to be the same number. That makes sense. But here's a set that's not quite symmetrical, close, but not quite, yet the mean and median are still the same. So interesting. So definitely know that because we have the focus now on 0, the mean is basically what we're doing is we're kind of translating the mean from 73 to 0 by doing this. So for these data sets, right? So I can change, although I don't know if I can change to orange, but maybe yellow. I don't know if yellow is going to show up here. Yeah, so the mean of the deviation, so x sub d, is going to be 0. And that's true in both cases. Which is interesting. So each difference is found by finding x sub 1 minus x sub 2 minus x bar, and so on and so forth, right? Just like we did. Here's the thing. If we were to add them up, we could add them up, divide by n, and what that would tell us is the average deviation. Well, wait a minute. Average deviation. So let's go back and take a look here. Average deviation. So I'm going to take these numbers and average them, right? So find their mean. Well, we already know that. It's 0. Because when I add them up, know how symmetrical they are. So add them up, and they're all just going to cancel out. Same thing here. Add them up, they're just going to cancel out to 0. And some of the numbers are negative, some of the numbers are positive, right? And that's because we subtracted everything to make the graph center on 0 rather than on 73. So, interesting that they add up to 0. Well, guess what? It turns out for a data set, that always happens. Every time that you take the data set, any data set whatsoever, whatever numbers, pick a bunch of numbers, doesn't matter, find their average, subtract that average from each individual number, decimals and everything, and then add all that up, and you will get 0 every time. So if the average deviation is 0, is this useful to us? Not really. Well, it's not useless in the fact that it allowed us to see how symmetrical the data was. So it kind of brings out the symmetry in the data. So it's not completely useless, right? But from a calculation standpoint, okay, so average deviation is 0. Okay, that didn't work. So, any suggestions? To deal with the 0 part, right? We hope that we want to find some kind of measure of deviation, some kind of average deviation. So what statisticians do actually instead is they square the deviations before adding them together. This creates something what's called the sum of squared deviations. The symbol for it is S with a subscript XX, and it references its sum of deviations squared. So the formula is exactly what the word is, right? So remember, this big E, that's sum. Sum of your deviations squared. And you just change the order for grammar, but essentially that's what you have. So what this is saying to do is to take all those numbers that we had, the orange numbers, square them, and then add them up. Well, why square? Because squaring gets rid of the negative sign, right? So some of you that are a little bit more astute at math might realize that, hey, what about absolute value? Wouldn't absolute value do the same thing? Well, yes, would. Absolute value will just strip off negative signs. There's a reason why we don't use absolute value, and we use squaring instead, and it comes out a little bit later on. So more on that. I'll say that after some deliberation, the gods of statistics from 100 something years ago, who first came up with this stuff, said that we should square the data points instead. Now, taking the absolute value does create something known as mean absolute deviation, which is a kind of different thing. So actually, there is a reason why we do squared, and we'll talk about that in future lessons. So for now, kind of trust me on this one that squaring is the order of the day, and that helps get rid of the negative signs. But we do need to turn this into an average, right? So dividing by n would create the average squared deviation, right? But, oh, okay. Ooh, this looks weird. Okay, so yeah, we're going to get into some pretty beefy formulas here. Now, good news. You're looking at this page wondering, what is this formula? Good news, guys. You won't have to do this by hand. Calculator takes care of this for us. What we're using this for is to kind of understand the necessity of this. Okay, so here's what we're going to do. What this formula is telling us to do is this deviation that we're doing, the squared deviations, right? We add them all up, and we divided by how many we have. Well, that's the definition of average, right? Except we're not dividing by n. We divide by n minus 1. Again, there is a reason for that. We're going to talk about that in a second, okay? So overall, here's the formula for standard deviation. So this is what we call sample standard deviation. Now, why the square root? So the reason for the square root is because all our data points have been squared. So if we go back up here, right, and we look at our data, this is all exam scores. But when I look at this formula here and I find the square deviation, what I now have is I now have exam scores squared, which, how do you square, like, what is a square exam score? Like, physically? I don't know. But it's a squared unit. So in order to do that, the square root removes the square and puts us back on same unit of measure. That's the purpose of the square root. Um, so what we're doing is we're finding like an average square and then taking the square root so that like, hey, now we can say what is that as an exam score, okay? And we always take a positive square root. And so what we have here is this thing called standard deviation. Okay, so in a little while, we'll kind of go over like, what is this thing? What does it do? Why do we need it? So we'll talk about that in a second. So actually, maybe we'll do that now. We'll kind of skip ahead. The slides kind of ended up a little bit out of order. So let's just go over exactly what this is, okay? So the standard deviation, which is either S or sigma. Now, lowercase sigma here. So this is the lowercase sigma. The big one, the curved E, is the uppercase sigma. So it's the Greek version of the uppercase s versus the lowercase s. The lowercase s we use for standard deviation of a population. Okay. So the standard deviation of a data set, what this measures is the mean distance that data points are from the mean. And it is a measure of the spread of a data set. So it really tells you how much data can vary from the mean. Because when you take observations from a data set, the observations aren't always at average, right? So the test scores aren't always 73. So what it refers to is how far the data points we'd expect they might vary from average. The higher the standard deviation, the more the points could vary around average. So here's a good thing to kind of visualize. Consider taking a new observation in the same population that you've been studying. Okay, these kids taking an exam. We know the class average is so far is a 73, but suppose that we take a new observation. A student who is absent takes the exam. Are they going to do a 73? Probably not. I mean, they could, but the likelihood is they're not an average student. They're either going to be above average or below average. And that amount that we'd expect them to be above or below average is approximately equal to the standard deviation. So we'll go ahead and we'll calculate that for that data set in just a bit. We're going to do it by hand, and then I'll show you how to do it in the calculator. But this is what it kind of looks like. So I'm going to draw a bell curve here. Okay, now let's do this in a different color. Let's do this in blue. Blue. Okay, so most normal data looks like this. Ooh, that is a funky looking bell. Let's get rid of that. Let's try that again. Most data looks like this, kind of like a bell curve. You know what? I need it bigger than that. To kind of really illustrate this, I'm going to make it like, there we go. There's my bell curve. Okay, so your average is here. Your mean, right? So most of your data is going to be near average. And this is true for lots and lots and lots of data sets. And notice here, this does assume the data set is symmetrical. Later on, we'll show that doesn't have to be true. But for now, most normal data is symmetrical. The mean and median are about the same. And most of your data is near average. So what happens is we're going to come over here. I'm going to draw a dotted line here. I'm going to draw a dotted line here. And we're going to say minus 1s plus 1s. So we consider this average. Now, we said earlier that average and mean I like to think of as two different things. So the mean is the exact center of the data, right? So here, the mean is exactly where that is. So for these classes, we had an average of 73. But average, or what we would consider to be average, is close to the mean, but is some range around it. That range is marked off by the standard deviation. So, for example, you get a 70, the average is 73. Student gets a 75 on the test. Would you consider that above average? Well, I mean, may exactly, I guess. It's 2 points above average. But those 2 points, that's pretty small, right? And if they get a 75 and they're above average, who's to say that maybe if they took the test a different day under different conditions, maybe they would have ended up with a 72 and been below average? So when a value is close to average and is within this range of what we'd consider standard deviation, right? When a point is within this range, it's close enough to average that under different conditions, if we looked at that point again, it could very well have been below average. And if we collect more data, points that are near the mean with more data, the mean and standard deviation itself could shift, and points that were below average before might end up ultimately being above average with more observations. So points that are in this range of what we call the standard deviation, um, they can sometimes, depending on the situation, they could either be considered above or below average um, as we learn more about the population, and they can flip back and forth. Once you get outside of that, it becomes much, much more difficult to justify that. So let's say you got a point over here. Let's say you got a student who doesn't do very well, and they're in this area down here. If they're more than one standard deviation from average, then they're far enough away from average that no matter what kind of further observations you take, or different conditions, or add data to the data set, a point that's here will likely stay below average, and a point over here will likely stay above average. We don't suspect that a point that is significantly above average would suddenly become below average. That's the whole idea here. So a point within one standard deviation is considered average range. Now, once you get more than two standard deviations away, right? And so if I marked off another one here, and I'll mark it in red, if I marked off another range here, now, I'm sorry, this graph is not exactly perfectly symmetrical, but bear with me here. If you get a point that's way out here, that's so far away, it's two values of standard deviation away. Those are pretty rare, so we might consider those to be outliers. And so this is your first major numerical definition of what an outlier is. But more of that will come later, right? Do keep in mind what this means is that nearly all points in a data set are going to be within two standard deviations of the mean. And that's actually true for almost any data that you could collect. So, um, any points that are far away, you can quantify that, say that they are pretty uncommon out there. Okay, so that's kind of the definition visually of what standard deviation references. So let's see how that applies to the data that we collected, okay? So let's look at these numbers, right? So let's start with class A. So we have, oh, some of these data is a little bit different. So let's go back up here um, to find the original one, right? So let's go back up here. These are our original values. I'm going to erase some of what we know, okay? So here's how you calculate standard deviation. Let's start, we'll just do this with class A. What you do is, like we did before, we found the difference from the mean. And that's taken with sign and everything, so that is x minus x bar. And we do that for each individual data point. So that's what these represent. But then the next part is we square them. And so 23 squared is 579. Nope, not 579, 529. Wow. Okay. Now I could use a calculator with this, sure. Is it 5? Yeah, 529. Okay. 144, 16, 144, 529. Okay. And so we square them all, right? Then the next thing we do is we add all that together. Okay, so now I'm going to pull out my calculator. Um, and so I'm going to pull out a calculator. I'm going to come down here and let me find it here. Ooh, look at this. I have a copy of the Inspire on my computer. Well, look at me, it be fancy. I know you guys don't have one at home. I'm sorry. But we're going to need to use this in order to learn how to work with it. So you're going to start seeing this a lot more in my videos as well. And I can also, if you have a TI-84 and you'd rather use that, I can always provide you directions separately on how to do all this work on a TI-84. But because I'm using this in class, I might as well use it here. So I'm just going to hit my calculation button. There we go. And you hit it twice, once or twice to make sure it's set to calculator. And I'm just going to go ahead and make sure. So let's do 23 squared just to make sure. 529. Okay, I did that right. So let's add all that up. So it's 529 plus 144 plus 16, and then we're going to multiply by 2. 1378. So this adds up to 1378. Okay, so the rest of the formula looks like this. We now divide by n minus 1. Okay, n minus 1. Now, you may be wondering, why not n? Okay, we'll explain that in a second. So we're going to divide that by 5. And so 1378, let's see, divided by 5. Oops. So 1378 divided by 5. Oh, right. We got to do that right. Okay, so hit enter. Whoops. 275.6. So this is equal to 275.6. And then what we do is we take the square root of that. The reason for the square root is we said these are now square exam scores. We take the square root to return back to just plain exam scores. And that will be, let's find that again, 275.6. Oops. Actually, I could just do square root. 16.6. So what this number is saying is that we would expect exam scores to differ from average by about 16. Now, let's look at that from the perspective of Class B, right? So from Class B, we have the same numbers, right? So we are going to take these numbers, square them. 81, 9, 1, 1, 16, 64. So now this time they're not perfectly symmetrical, but that's okay. I'm still going to add them up. Oh, and so this time I have 81, 90, so that's 90, and then 90 plus That's 80, so that is 172. Okay, and then we're going to divide by 5, and then we're going to take the square root of that. Okay, so let's do that here. So 100, so we're going to do a square root. I'm just going to make this quick here. So square root of 172 divided by 5. And whoa, holy simplify of radicals, Batman. This calculator is good, I'll tell you that. Let's do a control enter on that. 5.87. Okay, about almost 6 points. Okay, there we go. So what's happening here is we have 16.6 for Class A and 5.87 for Class B. So this is a measure of how much we'd expect the points to vary. Now, do the points vary by 6 in this case, or by 17? No, it looks like it's less than that. So remember, this is an average deviation from average. So remember, your average is 73, right? So if you think about it, some of these points vary by, here's this one varies by 9, this one varies by 3, and by 1. And when you look at it and you take all of those numbers together, we're creating a sort of really what it is, it's a geometric average of about 6. So kind of interesting. So what does that mean? Okay. That means if we go back and now we can use this and go back and look at the chart that we had, and that was, sorry, my slides are a little out of order here. This one. So now, if we look at the classes, we can now place them on here like that. So if I draw another one here, okay, 73. So for class A, the standard deviation was about 17. So because it's about 17, we can add 17, and we're also going to subtract 17 as well. And we're going to look at this and say, oh, 56 and 90. So average range for class A is in between 56 and 90. Well, that's a huge range of scores, right? Now, that's just because the scores for that class happen to be so large. And if we look at them, 56 and 90. So scrolling back up here, I know. So if you look at that, 4 of the scores are within that range. 2 of them are not. So the top score and the bottom score are not in that range. So they're definitely significantly above and below average. But the others, despite the fact that they are a pretty wide range in and of themselves, all 4 of those points would be considered average range. The same thing is true for Class B. If we go down, we look at Class B. Oops, here we go. So if we look at Class B, so let's do this one in a different color. Here's Class B. The standard deviation was about 6. So the average range for Class B is in between 67 and 79. Okay, so any score in there is considered to be close enough to average, right? And if a new student were to come into class and were to take this test, right? Let's say maybe that absent student comes in. If they're above average, I would expect them to score maybe about a 79. And if they're below average, I might expect them to score about a 67. Now, obviously, will they get those scores? No, but that's a prediction that we could make. And we don't know until they take it, right? So that's really what standard deviation is all about. Okay, that pretty much covers a lot of the meaning of standard deviation. Um, so now what we can do is answer one final question here. What the heck is up with the x n minus 1? Okay, so we're creating an average, right? Standard deviation is a mean deviation. So why don't we divide by n, your sample size? So remember that our goal of selecting a sample, which we hope is a random sample, right? We do that from a population and we're estimating the stats of the whole population. That does also include not just average, but also standard deviation as well. When you select a sample, remember that we said that if you select a good sample, the average of the sample should be pretty close to the average of the population. So, like if I took a sample of students, or like remember we thought about the community service, right? So the average, community service should be, barring outliers, should be pretty close in my sample than it is to the whole population. Standard deviation, though, is different. When you select a sample, the range of values in the sample will almost always be smaller than the range in the whole population. Do you see why? It's because the only way to get the entire range is to select the highest and lowest points in the population. So, for example, like again, think about test scores in class. If I want a sample of your test scores, the sample of test scores will have a smaller number, yes, but a smaller range than the entire class because the only way to get it to match is for my sample to have the highest test score and lowest test score. And my range of my sample can never be bigger than that of my population, right? But your mean could be bigger or smaller. So standard deviation is what we call a biased estimate. It's because when I estimate it with a sample, it always ends up smaller than it should be. And therefore, it gets undervalued. So, what statisticians have done is they've bumped up the value by dividing by n minus 1. So, remember that dividing by a smaller number makes something get bigger, right? Smaller divisor equals bigger piece. So I don't have a hard and fast rule here. Literally, the reason for the n minus 1 is because statisticians said so. Which I know I wrote on your test recently that that's not an appropriate statistical reason. But in the beginning of stats, when they had literally nothing else to go on, it was what they had. And so statisticians just looked at it, and what they did is they compared the standard deviations of samples to the standard deviation of the entire population. And it turns out that dividing by n minus 1 increases the sample just enough to be pretty good estimating the population standard deviation. So that's why we do it. Um, is it perfect? I don't know. Don't think it's perfect, but um, it is definitely far better than just dividing by n. And after playing around with different things, this is the one that stats people said gives the best results. Now, can we at least justify it though? Yes, we can. And remember what I said before, the best defense is a good justification, right? So we still have to justify even at the beginning. So consider the original classes with a mean median of 73. If we didn't know the students' scores, then all except one of them could freely change. Now, what do you mean? It's because if we know that the mean and median has to be 73, right? Then the first scores, the first 5 scores can be whatever, right? But that 6th score has to make sure that it's the right number that causes everything to add up to exactly 73, right? So You could have 5 people get 100, but then this person has to have a very particular score in order for that average to be exactly 73. Um, Actually, in that case, 100 won't work. But like if everybody gets an 80, then this score would have to be such that lower that it causes the average to be exactly 73. So what that means is that the last point isn't actually random when we talk about mean and median. It's because if you already know what the mean and median are, which we're estimating that based on the population, right? So if we're assuming that the mean and standard deviation from our sample is about the same as the population, then only 5 of the 6 points actually truly vary. And that's why we divide by n minus 1, because we're trying to see what the deviation is among the 5 that can vary. We have a term for this in stats, and we call this the degrees of freedom. And you're going to see this a lot. It's the situation that in order for the sample to match the population, the last data point has to be such that whatever the first 5 are, whatever the whole bunch of data, the last point has to be specific to get the mean and standard deviation to exactly 73. Mean and median, and yes, even the standard deviation. So that means this last point actually isn't free. We call that, so that's why there's one less for degrees of freedom. Okay? So, guys, this part's technical. So, do you have to really know this? No. So, kind of there, kind of for flavor. I probably should have warned you at that at the beginning, but just kind of letting you know that why it's here. So remember, in stats, we're all about justifying. So, we have a formula, and this video serves to justify the usage of it. Okay, so finally, the last thing that we can do here, and again, here's the slide again, um, is looking at how to do this on the calculator. Okay, so obviously doing this by hand is going to be a pain, especially if you've got a lot of points, right? So here's some directions, and I'll just kind of show you how to do this on an Inspire. So let's pull up the Inspire, okay? Let's say you're here, you turn it on, right? You turn it on. All right, so regardless of what screen you're on, you hit the on button, and what you can do is you can do, actually, I'm curious here. If I put a little bit on this, if I press the menu button, and I do actions, insert, no, okay. I was looking at something else. Okay, hit the on button, and we'll scroll down, and we'll use add lists and spreadsheets. So it's this middle button here. It looks teal, and it looks like a Google sheet actually. And what that does is it's going to add a spreadsheet to your sheet. Now, in my case, we have a 1112. Let's delete that actually. So you see what it looks like from your perspective. Add lists and spreadsheet, and you should see something like this. 1.1. If you see a 1.2, that's okay. It's all really kind of the same. So you'll see this. Now, the lovely part is from here, you can view the document like this again on these calculators, and it has spreadsheets and calculations and stuff. And it's all super neat how we can add pages to these documents. So more on that later. But you're on this screen now. We've added a list and spreadsheet. Let's go ahead and type in some data. So let's type in one of our calculator ones. So let's see. Let's do this example here, 49, 61, 69. Okay. So let's do that here. So 49, 61, 69, 77, 86, 96. Okay. So here's my class of 6 people that have taken this exam. Similar scores to the last one, slightly different, right? Okay. So now we want to look at what we can do. So the next thing you want to do is you want to scroll up and you want to select column A, right? Now, it doesn't really matter what column it's in. But here's the other thing. It has to have a name. Okay. Unfortunately, the way it works and the way I was taught how to do this is you do have to give it a name. So I'm just going to physically type in exam. You give it whatever name you want. You could call it noodle if you want, whatever. Okay. This line we're going to leave blank. Okay. Notice here, um, it's goes away from italics, and now it's just normal print. Perfect. Okay. Here's my data. Suppose I want to find some summary statistics about a data set. All I got to do is press the menu button, go down to statistics, stat calculations, and one var stats. Okay. It's going to run you through a list of options, number of lists. I only have one list. Uh, most of this, again, you're not going to touch. Frequency should be one. Categories like this stuff, don't worry about. We'll never really use it. Um, our data list is A. It's column A. And first result column is B. That means all the data is going to go into B. And there we go. Now here's a lovely part on the calculator. There is a way to click and drag and open them up like this, which is kind of neat if you want, but it's not completely necessary. Look at what you have. The mean is 73. Here's my sum of squares, sum of data set. Here's my standard deviation. For this particular class, it's 17.02. Okay, now do note here that there are two different standard deviations that you're going to see. The one we will use most is SX. This is the standard deviation assuming that the data you put in is a sample. So we call this the sample standard deviation. The other one is the population standard deviation. This assumes that the data you put in is a population. This divides by n instead of n minus 1. We actually don't really use this one often because most of the data that we take is a sample, not a population. Okay. Now, if we scroll down here, you're going to see some other things you might recognize. Quartiles, we're going to learn about that, kind of review that next lesson. N, so N is 6 data points. Median, 73. And here's an interesting one, sum of squared deviations. This is part of the calculation for standard deviation. Okay, but anyway, the most important numbers on here are the average 73, standard deviation, median. Perfect. Okay, and that's how you do it on the calculator. Now, if you want to clear it out, you decide you don't need this anymore, you could just go back up here. I think if you hit up arrow a bunch of times, it can highlight the whole thing, and then just hit delete. Go over here, just clear out your data, and you're done. Okay, perfect. There you go. And that's how you find some of the summary stats on the calc. Okay. All right, so I think that's about it. If you need anything else, just let me know in class. You can now work on the lesson 2 problems. Should be pretty easy enough on whatever calculator you happen to have. Just let me know if you need to learn how to do it on another calc. All right, have yourself a lovely evening, folks, and take care.